In the last lecture, we saw how circuits are represented with circuit symbols. In reality, circuits can be quite large, containing millions of circuit components. So without some structure, we are bound to get lost. In this lecture, I will help you understand how to read circuits and give you some simple rules which will always keep you in check even if you are dealing with a large circuit. So first off, wires. Wires are just conductors with very low resistance. But for simplicity, we just assume wires have no resistance at all. This makes our computations a lot easier. Let me show you what I am talking about. Let's say this wire is carrying a current of 5 amperes. Now, we can apply Ohm's law to figure out the voltage difference between the two ends of the wire. And putting in the values, we will get the voltage difference to be 0 volts, since the resistance is 0 ohms. In fact, whatever the current is, 5 amperes, 10 amperes, or whatever, because the resistance is 0, we will always have 0 volt voltage difference between the two ends of the wire. Keep in mind, the voltage difference is 0, not the actual value of the voltage. For example, if we knew that the voltage on one side is 2 volts, we would immediately know that the other side must also have 2 volts, because this way the voltage difference will be 0 volts. Or if the voltage on one side was negative 5 volts, the other side would also have been negative 5 as well. If one side of the wire had X voltage, the other side would also have X voltage. That's what it means for the voltage difference to be 0. And not just the endpoints, you could say the same thing about any point within the wire, because there is no resistance between the, say, middle point and either end of the wire. In fact, you can say the same thing for the wire as long as it extends. So, in summary, the wire has the same voltage everywhere as far as the wire continues. It was possible because we had assumed the resistance of the wire to be 0. If there was some resistance in the middle of the wire, this would not be the case. Say there was a 5 amperes of current and we had a resistor of 10 kilo ohms. We would definitely have some voltage difference between the two ends of the resistor, resulting in different voltages on either side of the resistor. But still, instead of one continuous piece of wire, now we have two continuous pieces of wires. The left piece will have one voltage everywhere and the right piece will have another voltage everywhere of that piece. In fact, we don't even need to put up any artificial resistor. If you just cut a wire, there would be air in between the wire pieces. And air being an insulator, which means air has a very high resistance, the pieces of wires will definitely have different voltages. This is how switches turn light bulbs on or off. When you switch something, the wire is cut off, and if you switch it back on, the connection is re-established. By the way, because air is an insulator, you are not getting electrocuted right now from the live power lines going right beside your home. Those cables hanging on electric poles are not protected by any rubber or plastic type insulators, unlike household wires. Those cables are totally naked, and if you touch one, you would instantly get electrocuted. And it's a good thing that air is an insulator, because if it wasn't, your body would have the same voltage as the 400 volt power line right beside your room. And you can imagine we would all be dead. So good thing air stops the voltage from reaching us. Okay, back to the point. So a continuous piece of wire has the same voltage everywhere. This will be our first rule. By the way, we have a name for a continuous piece of wire: node. Let's take a look at our trusty old basic circuit and see if we can identify the nodes. But first, let's represent it with circuit symbols. As you can see, this circuit has two continuous pieces of wires. That's why we say this circuit has two nodes. That's how we identify nodes in a circuit. Each of the nodes will have exactly one voltage. Let's see another example. See if you can tell how many nodes this circuit contains. This circuit has 3 nodes, that is 3 continuous pieces of wires, and each of these nodes will have different voltages. For example, this bottom node might have 4 volts everywhere, and the other nodes will also have some other values of voltages associated with them. So I like to call the first rule one node, one voltage rule. Every node will have exactly one voltage associated with it. Okay, that's all about wires. Now let's talk about circuit components. By circuit component, I mean anything that we connect in an electric circuit other than wires. For example, both resistors and voltage sources are examples of circuit components. There are thousands of electric components, so it's not possible to study all of them individually. Here, I will be discussing them in a way that makes sense for any electric component. Every circuit component has terminals. Terminals are basically nodes where we can connect wires or other components. A circuit component can have quite a few number of terminals. For example, if you ever heard about transistors, they have 3 terminals. But in this course, we don't have to worry about more than 2 terminals. For example, resistors and voltage sources have 2 terminals. So they are 2-terminal devices. Since terminals are just nodes, each of them will have a voltage associated with them. Also, since electrons just pass through the circuit components at a steady rate, we will have a single current going through the components. Remember, electrons are negatively charged, so the direction of conventional current is the opposite to their direction of movement. So, this is our second rule. You will have one current for every component. Oh, and by the way, since we have just 2 terminals here, we call them positive and negative terminals. Whenever you need to calculate the voltage difference, always remember it's the voltage of the positive terminal minus the voltage of the negative terminal. And also be careful about the direction of current. It should always be from positive to negative terminal as well. This system is what we call passive sign convention. It's a convention that says it's okay whichever terminal you want to call positive or negative, but the direction of current must go from positive to negative. If you don't know what a convention is, it basically means something that is not a universal law but everyone agrees on, so that we can avoid misunderstandings. For example, there is no universal law stating which side of the road you should drive on. That's why some countries like USA drive on the right side of the road, whereas some countries like ours drive on the left side of the road. Whatever the case, as long as everyone in a country drives on the same side of the road, there will be less accidents. So, driving on the left side is the convention in our country, and if everyone follows this convention, we can prevent a lot of accidents. In the same way, passive sign convention makes sure we don't run into an accident. So, always follow passive sign convention. Okay, so now we got 2 golden rules that applies to any electric circuit. The first one says you will get 1 voltage for every node in your circuit. And the second one says you will get 1 current for every component in your circuit. In fact, you will also have 1 equation for each of them as well. Let's look at an example. And also, while we are at it, let's use positive charge instead of negative charge electrons, because it's always a pain to think in the opposite direction. Representing this circuit using symbols, this is what it looks like. Basically, you have the same current throughout the circuit flowing in a loop. Let's focus on just the resistor. For this one resistor, we should have 1 current and 1 equation. And of course, don't forget to follow the passive sign convention. Because the current is flowing from top to bottom, the top terminal will be the positive terminal and the bottom terminal will be negative. Let's give this circuit some values so we can take a better look. This circuit has 2 nodes. Let's say the top node has 6 volts and the bottom node has 4 volts. Okay, so what will be the voltage difference? Remember, always positive terminal minus negative. So we have delta V equals 6 minus 4, 2 volts. I also promised there will be an equation associated with every component. So what equation is associated with resistors? The answer is Ohm's law. Of course, because Ohm's law is only applicable to resistors. You can use this equation to figure out the current. You can also calculate the power from these values. So after some calculations, we have 0.2 amperes of current in the downward direction and a power of 0.4 watts. That's all good, but what if we almost made a mistake? I mean, looking at this circuit, we could easily say the current was in the downward direction. But what if you thought it was in the upwards direction? This actually might happen because in larger circuits, it's often harder to figure out the direction of current. And of course, in real-life circuits where there are thousands of circuit components, it's nearly impossible. So, it's reasonable to think that you might assume the direction of current in the wrong direction. Let's go with it and see what happens. Maybe following the passive sign convention will save us. Okay, so now the current is going from bottom to top. So according to passive sign convention, the bottom side is the positive terminal and the top side is the negative terminal. Let's do the same calculations. Using the definition of delta V, this time we will get 4 minus 6 equals minus 2 volts. Well, that's expected because we flipped the positive and negative signs. Let's use the Ohm's law to figure out the current. We get negative 0.2 amperes of current this time. So what will be the power? Inserting the values, we get 0.4 watts of power. So after some calculations, now we have negative 0.2 amperes of current in the upward direction and a power of 0.4 watts. Now let's compare this result with the results from previous attempt. Well, we get the same power, so that's all right. But the current doesn't seem to match. Except negative 0.2 amperes of current in the upwards direction is the same thing as 0.2 amperes of current in the downward direction. So we actually got the same result, but in a different language. That's the power of passive sign convention. Even though we almost made a mistake thinking the current is going in the upwards direction, it gives us the correct result either way. That's why you should always follow this convention. In fact, this example also emphasizes why you should consider negative currents. In my opinion, treat all numbers as equals. Negative numbers are also just numbers. Now, let's take a look at the voltage source because just looking at one part doesn't always give you the full picture. In fact, one look at the voltage source will present us with a dilemma. Let's just pick one of these and start working on it. So we have 0.2 amperes of current going in clockwise rotation through the whole circuit. Focusing on just the voltage source, we have a current of 0.2 amperes in the upwards direction. But what's different this time is the voltage source already comes with a positive and negative terminal of its own. For example, in a battery, you always see there's a positive sign on one end and a negative sign on the other. But this just created a problem for us. This positive and negative sign and our direction of current does not follow passive sign convention here, hence the dilemma. But don't worry, you basically have two options. Either go with the positive-negative terminal and flip the current to follow passive sign convention, or go with the direction of current and flip the positive-negative signs. Both of them will give you the correct answer as long as you follow passive sign convention. I personally like to keep the positive and negative sign in its place. So now let's do some usual calculations using that. We get a voltage difference of 6 minus 4, 2 volts. And now for the component equation for voltage source. What will that be? It's not a resistor, so Ohm's law does not apply to it. Then what is it? Well, actually, it's the last equation, delta V equals 2 volts. Believe it or not, this is the equation for voltage source. So we don't get 2 from 6 minus 2, rather it's actually the other way around. Usually we are given only one node voltage. Say we know the lower node has 4 volts of voltage, but we don't know the top one. Right beside the voltage source, it will be labeled as 2 volts, which means it creates a voltage of 2 volts between the two ends of the component. So, whatever happens, this voltage source will always maintain 2-volt voltage difference between its two ends, even if that requires a huge amount of power and current. That's why delta V equals 2 volt is the component equation for voltage source. Now, how do we figure out the voltage of the top node from this? Well, let's say it is X volts. Now, according to the definition of delta V, we have 2 equals X minus 4. Doing a little manipulation, we have X equals 2 plus 4, 6 volts. So there you go. Now, what about the power? Using the definition, we have P equals 2 times negative 0.2, which is equals to negative 0.4 watts. And as you can see, we get a negative power. This negative sign also tells us something important. So in the case of resistor, we got 0.4 watts. And in the case of voltage source, we have negative 0.4 watts. So positive power actually means it will consume the power and do something else with it. For example, light bulbs and irons are resistors and they consume electric power and turn it into light and heat energy. On the other hand, negative power means it supplies electric power to the circuit. For example, voltage source was supplying power to the circuit. The battery in your remote control supplies power to the electronics. So it's really handy when you can just see whether the power is negative or positive and can instantly tell whether it's supplying power or consuming power. By the way, just like we have seen voltage source up to this point, we also have something called current source. So the equation for voltage source is just delta V equals the leveled value of the voltage source, which just means whatever happens, it will keep the voltage difference exactly 2 volts. For current source, the equation is almost same, except it's for current. So what I equals 3 amperes means is that whatever happens, it will make sure the current through that current source is 3 amperes. Nothing more, nothing less. Now I want to introduce you with one more symbol. Just bear with me for a second. In this example, we saw if we knew one node voltage, we could calculate the other. For example, if you knew the bottom node was 4 volts, we could calculate the top voltage to be 6 volts. If the bottom node was 3 volts, the top node would be 5 volts. If the bottom node was 0 volts, we would have 2 volts for the top node. And almost always we are given 0 volt voltage for one of the nodes. That's why we have a symbol for 0 volts. We call it the ground symbol. That's because the earth has a voltage of 0 volts. When we talk about the earthing in our homes, this is what we are talking about. It just means the node it's connected to has a voltage of 0 volts. There's nothing more to it. So this has been a long lecture. Unfortunately, I couldn't find a good way of breaking this down into multiple videos, but hopefully you got the gist of it. For your convenience, here's the takeaway from this video. Make sure you understand them. Thanks and see you in the next lecture.